I'm now going to take you through the bioethanol production from biomass. We got to bear in mind that not all types of biomass will be sustainable. The biomass of choice should not conflict with food and feed production or nutrient retention in the soil. This is important, that the biomass should be truly, in true sense, should be waste material that can be converted into added value products to benefit society. And that biomass, if it is a waste, then it will not conflict with land use. And if that biomass is burned in open air, then it will cause pollution to the environment. If that biomass is a landfill because it's a waste material, it will also cause emissions and environmental impacts. So we have to be always mindful about the choice of biomass, that it should not conflict with food, feed production and soil nutrient retention. And the biomass should be truly waste. And if that biomass is used for product generation through a process, then that process should be sustainable if process integration is formally applied. And we are going to see here an example of bioethanol production from such waste biomass. The references, the first one is a paper in Bioresource Technology Reports, Economic and Environmental Impact Evaluation of Various Biomass Feedstocks for Bioethanol Production and Correlations to Lignocellulosic Composition. The work has been done between the UK and Mexico, and the biomass that we considered are in excess, and they're basically burnt in open air to cause emissions and impacts, environmental impacts. Those biomasses are available in Mexico, and these can be turned into bioethanol. And bioethanol, as you all know, is a petroleum additive. 100% bioethanol car can also be possible, but presently mostly 5 to 10% by energy bioethanol is blended to conventional petrol. And you can read this paper on the policy drives, policy aspects, the different types of petrol produced by different ratios of bioethanol in petrol. This aspect has been discussed in this paper. The paper also does the whole range of environmental life cycle assessment of bioethanol compared to fossil-based petrol production systems. And also it does the economic evaluation, that is microeconomics, that is the capital cost estimation, operating cost estimation, the product value estimation, the cost of production, discounted cash flow analysis, break-even point, and payback analysis, etc. And in the technical analysis from biomass throughput, we can calculate bioethanol produced production, and also combined heat and power production, and the efficiency, such as energy efficiency. The experimental basis is given in the reference number 2 from National Renewable Energy Laboratory, number TP-5100-47764, and this paper is also available on internet, nrel.gov/docs/FY11OSTI/47764.pdf. This work also involves Aspen Plus simulation of the complete heat integrated flow sheet, and in the next slide we are going to discuss the process integrated flow sheet for bioethanol production utilizing waste biomass. The following two papers by one is in collaboration with Malaysia on Sago biorefinery systems. Sago biomass, once again, it's X's, and we used one for bioethanol production and energy systems, and the other paper is on combined heat and power generation. And the final is a book written by me and my PhD graduates, Coxiu and Elias, Biorefineries and Chemical Processes, Design, Integration and Sustainability Analysis. This is the most complete book on biorefinery, bioeconomy systems of present times. The block flow diagram for bioethanol production. First, raw feedstock is taken to A100 feed handling step. Feedstock is produced. Feedstock is usually a lignocellulose material, therefore pre-treatment is needed to first break hemicelluloses apart so that celluloses can be extracted and lignin can be separated because lignin hinders the fermentation process. Hemicelluloses and celluloses are the polymers of C5 and C6 monomers sugars, and these needed hydrolysis and fermentation to generate bioethanol from glucose. In the pretreatment stage, ammonia, steam, acid are used. And as said, that pretreatment is to extract the celluloses, hemicelluloses from lignin. The hydrolysate, which is the soluble part, is taken to enzymatic hydrolysis and fermentation process unit A300. An enzyme which acts as a catalyst to fermentation is produced from glucose and nutrients. Cellulase is the enzyme that is manufactured by a culture, and cellulase acts as catalyst for enzymatic hydrolysis and fermentation process. Obviously, to maintain the culture, bacterial culture, we need nutrients to the enzymatic hydrolysis and fermentation unit. From the unit, the main product is the bioethanol or beer and some vent, and also there'd be some vent in the following process, which is the separation and recovery of bioethanol, and the bioethanol product is stored in A700 storage system. A500 is the separation units, distillation, dehydration, and solid separation. The final process could be adsorption, such as molecular sieves, to get really high quality bioethanol, 100% bioethanol. And then 100% bioethanol cars are available these days, and so which means our cars can be on 100% bio-based petrol, but also bioethanol can be blended to the gasoline or petrol product. The distillation needs steam input. The stillage or the wastewaters are generated that are taken to A600 unit wastewater treatment. The lignin fraction is taken to the burner, boiler or turbo generator, the combined heat and power system, and we have previously have a video on this system. There would be other auxiliary fuel if needed, and the idea of this combined heat and power generation system is to generate steam and electricity. The biogas will be generated from wastewater treatment and routed to this combined heat and power system. In the wastewater treatment, there will be first some conventional wastewater treatment unit followed by anaerobic digestion, and anaerobic digestion will generate the biogas. Water recovered can be recycled water can also be evaporated, and some flash condensate will come from the pre-treatment unit to wastewater. Obviously, wastewater, because we are having anaerobic digestion, the organisms should be fed with nutrients. And thus the input to the system would be ammonia, steam, acid, obviously some nutrients to maintain the culture, and also the biomass, which is the core for the production of the bioethanol system. The design basis in the National Renewable Energy Report is 2,000 metric dry ton biomass processed per day. And if a wet biomass contains, say, 25% moisture by mass, then the total wet biomass processing in ton per day is 2,000 times 100 divided by 75. That is equal to 2,667 tons per day of wet biomass. Operating number of hours per year assumed are 8,410. Then from there, annual wet biomass processing or throughput in ton per annum can be calculated. And then annual dry biomass processing in ton can also be calculated. And these values are around 930,000 and 700,000 tons per annum, respectively. Why do we need the calculations? Is to estimate, first of all, mass balance. Also looking at the energy analysis, energy balance, primarily bioethanol yield and combined heat and power yield. The process could be a net sink of combined heat and power. In that case, we really can't generate any additional heat and power. All will be used, and some additional steam may be used by the site. And in that case, there is no energy output, only bioethanol output. But that really depends on the biomass constituent. And we are going to look into the biomass analysis, and from there try to estimate the compositions of the various products, including bioethanol as the main product. And also then we're going to estimate global warming potential saving, and also we're going to carry out economic analysis of the plant to see the economic viability of the plant. An example of biomass composition is here. The weight analysis in percentage of waste wood. Cellulose, 29.4% on a weight basis. The following chemicals, xylene, glucan, arabinan, mannan, galactan, comprise the hemicellulose fraction, and their percentage mass in the waste biomass is 20.4, 4.8, 0.5, 0.5, and 0.5 respectively on weight basis. Lignin content is 18.7% of waste wood. Ash is 1.5% of waste wood by mass. And moisture by mass is 23.7% of waste wood. Now the conversion rates, because we got to understand that how much of the constituents, biomass constituents, is actually converted into bioethanol. And this is to look at primarily the bioethanol product yield. In the rows, you are looking at the various types of products generated from the pre-treatment process. Basically, these will come as one hydrolyzed stream, and within the hydrolyzed, the various components will be present, which are xylose, farfural, oligomer, glucose, hydroxymethyl farfural, arabinose, mannose, galactose. And these components are generated from the constituents in the hemicellulose. And as we have seen in the previous lecture, that pre-treatment process actually attacks the hemicelluloses to generate the various streams, the various water-soluble streams, so that the cellulose part and the lignin part are separated. And as you know, lignin hinders the microbial degradation. Therefore, lignin has to be separated from the enzymatic hydrolysis and fermentation process in order for microbes to allow breaking down further these nutrients, these substrates into the products, and the product here, target product here is the bioethanol. The various columns represent the biomass constituents. Basically here in the pre-treatment stage, hemicellulose components: xylin, glucan, arabinin, mannan, galactan. And the values in different tabs show conversion rates of the component in the hemicellulose into the product in the hydrolyzed from the pre-treatment process. For example, 90% of xylin present in hemicellulose is converted into xylose. Five percent of xylin is converted into farfural, and 2.4% of xylin is converted into oligomer. Similarly, glucan is converted into oligomer, glucose, and hydroxymethyl farfural by 0.3%, 9.9%, and 0.3% respectively. And similarly, you can read the rest of the table. Farfural and hydroxymethyl farfural are further actually converted fully in the pre-treatment process as tar, and tar is the insoluble output, and therefore tar will be separated out from the hydrolyzed. The tar actually goes to the combined heat and power system, which is not shown in the NREL flowchart. Then the enzymatic hydrolysis step, where cellulose is converted into glucose oligomer cellobiose by 90%, 4%, and 1.2% respectively. And cellobiose produced, that is 1.2% of cellulose, is fully converted into glucose 100%. All these conversion rates are given on mass basis. Then the fermentation is the core process, and the product is primarily ethanol. Ethanol is produced from glucose, xylose, arabinose in the feedstock. 95% of glucose, 85% of xylose, and 85% of arabinose are converted into ethanol. The product stream also contains zymo, glycerol, succinic acid, and xylitol. Therefore, this outlet stream is taken to the separation unit. The separation will comprise distillation and molecular sieve. The steps are also to break any azeotrope, and ethanol and water form actually azeotrope in the column. Assume ethanol recovery by 98% by mass in the separation process. The design basis: the balance of the organic components goes to the wastewater treatment along with the water stream. Calculate this balance from the amount of organic compounds. that is equal to total wet biomass subtracted by moisture, ash, bioethanol, lignin, and tar. Bioethanol is obviously the main product, which is 100% after the separation unit. And any stillage stream will be routed to the wastewater treatment. Ash is insoluble, therefore it will be extracted from the pre-treatment step. The moisture also goes out to the wastewater, and moisture can be returned to the pre-treatment process. Lignin and tar are insoluble, and therefore these are routed to the combined heat and power generation process. So using this simple equation, you can calculate the amount of organic that goes to wastewater treatment. And wastewater treatment comprises conventional processes. After that, anaerobic digestion, where actually organic matter, these organic components, will be converted into biogas. We assume 30% by mass of this balance ends up as biogas, which has a calorific value of 23 megajoule per kilogram. And using this, we can calculate the mass flow rate and the total energy content of biogas. Now for the combined heat and power system, which will take up lignin, tar, and biogas, we can calculate the total energy input to the system. Lignin has a calorific value of 23.5 megajoule per kilogram. Tar's value is 36 megajoule per kilogram, and as you see, biogas calorific value is 23 megajoule per kilogram. So from the respective amounts of lignin and calculated amount of tar and calculated amount of biogas, we can calculate the total energy input to the CHP system. Now, we have already seen the CHP system configuration in previous lecture, which will comprise a biomass boiler and a steam turbine. We can assume a boiler efficiency of 90%, that is combusting lignin, tar, and biogas for the generation of steam. And from this, we can calculate the total energy content of the steam generated. Steam requirement by the site is 13.6 and 15 gigajoule per ton of bioethanol produced from agricultural and forestry biomass respectively. Applying these two numbers, we can calculate the amount of steam required by the site. And then this steam requirement can be fulfilled either partially or fully by the combined heat and power system. If the combined heat and power system can fulfill this amount of steam required by the site and still can generate some excess steam, then the excess steam can be expanded in a steam turbine producing electricity at 35% energy efficiency. Hence, we can calculate the amount of electricity generation. In contrary, if the site requires more heat than the production from the combined heat and power system, then we obviously can't generate any more electricity. We can't have the steam turbine. We just have then the biomass boiler to generate the steam, and any excess steam requirement should be met by importing steam to the site. So you can see that the energy efficiency will vary depending on whether the site requires any excess steam that should be fulfilled by importing steam, or if the site makes more of electricity alongside the bioethanol. Actually, the determining factor is the content of lignin. More the lignin, less is the cellulose, hemicellulose, and thus the sugar or glucose, and thus the amount of bioethanol produced. So more lignin means more combined heat and power generation, and thus excess electricity generation after fulfilling the site steam requirement. And less lignin means more bioethanol production and steam import to the site. And thus lignin content is really important in determining the energy efficiency and switching, whether you are looking at the cogeneration of bioethanol and electricity, or you are just looking at bioethanol generation with some steam import. Thus from lignin content we can have an idea of how much of bioethanol we can generate and how much of electricity we can generate, or how much of steam should be imported to the system. It's so very critical. And physically, actually, lignin protects the plant from microbial degradation. And when we use for anthropogenic purposes, then we try to destroy or separate lignin so that microbial attacks are possible on these polymers, cellulose, hemicellulose, biopolymers, so that glucose can be generated and that can be fermented into bioethanol production. So you can also calculate the energy output from the integrated system if you consider bioethanol heating value as 29.7 megajoule per kilogram. In the current policy landscape, the final use of biomass for energy and transportation fuel is considered to be carbon neutral. And this is true because direct biogenic emissions from biomass end use are captured during growth, completing the carbon cycle. In this case, we are generating bioethanol, which has the primary application as fuel, as transport fuel, and when the fuel is burned, then carbon dioxide is released to the atmosphere, but that carbon dioxide will be captured during the growth of the biomass. And thus, it is a full carbon cycle, which is much faster than the non-renewable fossil resources based cycle. If energy needed by biomass conversion process is supplied renewably by on-site generation, then emissions caused by burning fossil-derived transport fuel can be eliminated by using biofuel. Emission factor of petrol that can be replaced by bioethanol is 3.2 kilogram carbon dioxide equivalent per kilogram. And based on that, we can calculate the annual global warming potential saving in kilogram carbon dioxide equivalent per year. So the performance calculation in terms of bioethanol yield can be correlated to can be applied to this factor 3.2 kilogram carbon dioxide equivalent per kilogram basis to calculate the amount of global warming saving in carbon dioxide equivalent per year. Important economic terms for economic comparisons between systems. The economic margin is calculated by the difference between value of products and operating cost and capital cost. Netback when feedstock cost is unknown is the difference between value of products and operating cost without cost of feedstock plus capital cost. Cost of production. When product price is unknown, then operating cost, including the cost of foodstock and capital cost, are added to calculate the cost of production. The cost components are capital cost and operating cost. Capital cost is primarily calculated from the delivered cost of equipment or the direct cost of equipment. Then indirect costs are calculated, working capital can be calculated, and from which total capital investment is calculated. Annual capital charge is assumed. An annual capital charge is applied to the total capital investment to calculate the annual capital cost. Operating cost is always calculated annually, and that consists of fixed and variable operating costs. Correlations between delivered cost of equipment and size. This is to show the economy of scale. R value is less than 1, suggesting that with increasing size, we get more of economic benefit. So the cost for a different size can be calculated for a base size and cost given. Size 1 is the capacity of the base system, and size 2 is the capacity of the new system. Cost of size 1 is the cost of the base system, and cost size 2 is the cost of the system under consideration. R is the scaling factor less than 1, showing the economy of scale. So from known cost and size data obtained from vendor, for a given size, we can calculate the cost of a piece of equipment. And this is how for the main equipment of the site can be calculated, and that comprises the delivered cost of equipment. But this cost can be outdated. Thus, we need to convert it to the present cost by applying a present index value using this correlation, and we apply chemical engineering plant cost index in the recentmost year to update the cost information that we obtained. Here the information for calculation of the system delivered cost of equipment. The main units are pretreatment, mechanical dilute acid treatment, hydrolysis and fermentation, bioethanol recovery, distillation, molecular sieve, wastewater treatment, solid separation, anaerobic digestion, and total cost of storage and CHP system. The base cost, base size are given. The units are also given, because remember, when we take the ratio between the present size and the base size, this value should be dimensionless so that we can estimate the cost, the delivered cost of equipment for the given size. The scale factors, as said, is less than 1 to show the economy of scale. That is, larger the size, we get the economic benefit. The base year is given, and the cost index for the base year is given. The cost index in 2014 is given, but from recentmost literature on chemical engineering plant cost index value, say in 2019 or maybe latest, you can obtain that value and update the cost information calculated from the cost size correlations. Furthermore, installation factors can be applied depending on the amount of instrumentations and other components around the main piece of equipment. For the total cost of storage and CHP system, we are going to use a ballpark figure here based on the size given, which is 2,000 metric ton dry biomass per day. The capital cost. So the delivered cost of equipment is calculated this way: solid processing, fluid, solid processing, and fluid processing. For these three different systems, we then apply the different factors for calculating the other cost items. Within the direct cost, the other items are installation, instrumentation and control, piping, electrical systems, buildings, including services, yard improvements, service facilities, etc. And their total factors are 2.69, 3.02, 3.6 for solid processing, solid fluid processing, and fluid processing systems respectively. So once you obtain delivered cost of equipment, you can apply these factors to calculate the total direct cost for the given system. Indirect cost includes engineering and supervision, construction, expenses, legal expenses, contractor's fee, contingency, etc., totaling to 1.28, 1.26, 1.44 as factors for solid, fluid, and fluid processing systems respectively. Working capital is 0.7, 0.75, 0.89 times the delivered cost of equipment for solid processing, solid fluid processing, and fluid processing systems. The total capital investment is thus 4.67 times the delivered cost of equipment for solid processing, 5.03 times the delivered cost of equipment for solid fluid processing system, and 5.93 times delivered cost of equipment for the fluid processing system. Annual capital cost is then calculated by applying the annual capital charge, which is assumed at 0.13, to the total capital investment. The operating cost, which has two main components, fixed operating cost, that's dependent on indirect capital cost, and fixed operating cost dependent on personnel cost, and the variable operating cost. Total fixed operating cost and variable operating cost is added and then factored by 1.3 to get the total operating cost. Under the fixed operating cost, that's dependent on indirect capital cost, the items are maintenance, capital charges, insurance, local taxes and royalties, 5 to 10%, 10%, 1%, 2% and 1% of indirect capital cost annualized respectively, and fixed operating cost items that depend on personnel cost are personnel, laboratory costs, and supervision and plant overheads. Again, it is factored with respect to personnel cost. Using these correlations, you then calculate the total fixed operating cost. You also have to calculate the variable operating cost. These two costs are added, multiplied by 1.3. That will give you the total operating cost of the system. As you know from previous graphs that the indirect capital cost depends on the delivered cost of equipment, and for the solid fluid system, this factor is 1.26 times the annualized delivered cost of equipment. The variable operating cost is then calculated considering the inventories, sulfuric acid, ammonia, DAP, caustic, lime, electricity and heat. The values are given in kilogram per ton product ethanol, and their prices are also given. And obviously, do not forget to consider the cost of biomass in predicting the cost of production and also predicting the economic margin. You can ignore the cost of biomass in case of calculation of netback that you will do by taking account of the product value and all other costs on an annual basis to give you an estimate on the margin that you can obtain per unit of biomass. Thank you.